if x2 is 0, then we get 0. If x2 is equal to 1, then we get whatever probability x1 is times q. So we may as well say that this is equal to probability of x1 times x2q. Probability of x1 equals this, so that's stage 2. Stage 3, probability x1 equals x1, x2 equals x2, x3 less than x3, x3 equals 0, that's 0 again, x3 equals 1, I get the probability of the sequence x1, x2 times q, for x3 being 0. And I can write that whole thing as probability x1, x2 times x3q. So we see the pattern. The pattern is, it's the probability of, at stage I, it's the probability of the sequence up to I minus 1 times xi times q. So f plus the last term, which is just the probability of the whole sequence. F of x1, x2, and so on up to xn is equal to the sum. So there are n stages here. Sum from I equals 1 to n of the probability of x1 and x2 and so on up to xi. Xi minus 1 times q times xi plus the probability of x1, x2, and so on up to xn. So the extended CDF is relatively easy to write down by this formula. Now what we need is we need F bar. Well, what F bar is, so remember how F bar was defined. When we have our CDF, and we plot it like so, this value right here is f of x. This value is f of x minus 1. And this right here, halfway between fx minus 1 and fx, is f bar. So what we can say, this interval here is p of x. So we can say that f bar is f x1, x2, and so on up to xn, minus half the distance between these two, which is 1/2 p of x1, x2, and so on up to xn. And then I can explicitly write that down using this formula. So if I take this and subtract 1/2 px1 x2 up to xn, I basically get rid of half of this. So I have plus 1/2 px1, x2, and so on up to xn. That's f bar. L of x is equal to ceiling log 1 over p of x plus 1. So I take this value, take its binary representation, and just take this many bits. So, where does the geometric interpretation of this come in? So I said there's a recursive geometric interpretation here, which is that I start with 0.0, 0.1, like so, and then I can bifurcate that into 0.00, 0.01, 0.10, 0.11, this. Where that comes from, okay, so what is this? This value is f of x. And for each of these intervals, actually it's better to look at this starting from the main one going to the second one. So this line here is f of point 0.1, that's right. So in other words, the interval of probability where all of the sequences start with the first digit 1 is there. Now, f of x is this. Pardon me? Oh, wait a minute.
Less than or equal to?
Less than or equal to. Yes, that's right, actually. It's point.
What would the top one be?
This is. Okay, just a second. Yeah, that is 0.0. It's 0.0 because it's less than or equal to. So that's right, it is 0.0, and that's exactly the point that I want to make. Everything that is beyond here, well, everything that's over here must be greater than f of 0.0. Now, this term here represents the f of 0.0 part. That's everything that is smaller than, that's everything that's smaller than what you start with. So this additive part basically gives you the base. So that's up to x minus 1, I minus 1. I, in this case, is just 1, so that's just the first digit. So that basically makes sure, this term basically makes sure that the first digit, all the probability of the first digit being smaller is contained. So this basically gives you the additive base right here. This term, you can interpret this as probability of x1, x2, and so on up to n minus 1 times the probability of n. So this length here is probability, can be interpreted as probability x1, x2, and so on up to xn minus 1. In this case, n is just 1. So the length of this is just the probability that x equals 1. And to that, we multiply p of xn. So we take the fraction of this that's represented by the second part. So here it's 0, and here it's 1. So basically we have a base here, and we add to that a scale factor to represent the length of this interval times the actual probability.